Hello, good afternoon. The title of my presentation is an open source Wi-Fi chip, what, why, and how. Some thoughts from our Open Wi-Fi project. My name is Xian Jun from ID Lab, IMEC, Ghent University in Belgium. Thank you very much for staying so late. I know it's tired, right, everyone? My original plan is to use this board to jam the Wi-Fi here to make you focused on my presentation, but the chair said here we don't have Wi-Fi, so it's useless. But you do realize how Wi-Fi is important, right? So a little bit background of the Open Wi-Fi project. It's open source 802.11 Wi-Fi IPGA or chip baseband design. We start internally around 2017 and put it on GitHub at the end of 2019. It's under AGPL v3 license. Our current focus is on the baseband. Currently, we focus on the digital baseband, so not analog RF yet. This is a simple timeline. You can check it later. Basically, we have been working on this for 7 years, and now we are trying hard to get resource to make a long-term roadmap on this. Here are some important links where to find out the technical information and some special features, and these are all the boards we support currently. We are not hardware makers, so all the boards are off the shelf. You can buy them anywhere else and run the Open Wi-Fi design. You might be confused if you search Open Wi-Fi on internet. There are two Open Wi-Fi projects. On the left is our Open Wi-Fi, focus on the Linux driver and the chip, the driver and the below. On the right is the TIP's Open Wi-Fi. They focus on the OpenWRT Linux distribution for the Wi-Fi router to do some cloud-based roaming management. So you know which project to take, right? Yeah, I will start from why, not from what, because why is always very important. It could be just for fun, right? We shouldn't underestimate this motivation because we all know what have happened right after Linux put the Linux publicly. Then I make a poll on internet, on Twitter and LinkedIn to ask people why do we need an open source Wi-Fi chip? First reason, just for fun. And second, better security and privacy. A third, help customize or optimize Wi-Fi. And last, education and research. Here are the results. On both sides, education and research are the top reason. And better security and privacy are the second reason. Yeah, on LinkedIn, there are equal options. But anyway, I think people do have reason, right, to go for it, although it's not for fun. So which make me suspect I'm a weirdo because I think for fun is really an important reason. I'm sure I am a weirdo maybe. So and on the Twitter, more people join the pool. But we all know the survivorship bias, right? We should protect the bullet hole area or non-bullet hole area. So I initiate another poll. Why we don't need an open source Wi-Fi chip. The first reason is reinventing the wheel. Second, we can't compete with a big Wi-Fi company. A third, we can't try the hardware as easy as software. Last, it's insecure because I'm afraid bad guy will use source code to do bad thing. So on the left, the Twitter, and on the right, LinkedIn. So both sides believe we can't compete with big company. I think that's a normal thinking. On the Twitter, I think the second reason is that people really want to try it, but realize you can't try it as easy as software, right? But on the right side, the security concern is the second reason. Maybe that's a normal reason for the Euro business and Euro businessmen. People do think it's kind of reinventing the view. And another interesting observation is that on Twitter, on top is the positive poll, on the bottom is a negative poll. More people go for the positive poll, much more than the negative. On LinkedIn, it's about half-half. I don't know why. Maybe it's due to my personal connection on the social network. Anyway, it's just for fun, made for this conference. So seriously, let's go for a real why. Okay, this is the very important reason for myself, but I can't use this reason to convince many commission or investors, right, or funding source. So I think the first thing I want to raise is about security and privacy. Because many people who are not familiar with Wi-Fi might think Wi-Fi is a very simple device. It's just a dumb device to offer you a connection. And a Wi-Fi chip is also very low cost, low price, right, compared to a 5G, 6G base station and cell phone. But actually, it's not the case. Low cost doesn't mean it's simple. Wi-Fi actually is a highly complicated heterogeneous computing system. This is a very recent presentation from the CCC, German CCC conference, GPN 22, made by Daniel. In this presentation, he introduced every aspect of Wi-Fi chip. Here's a typical block diagram of a Wi-Fi chip. There's a host interface, PCIe, some ARM CPU, real-time CPU, 5 fabric, and of course radio or RF part, right? I also put what kind of processing or processors will be done in each block. There will be a microcontroller, CPU, real-time cores, of course also digital signal processing fabric or digital signal processing or digital signal processors. At the end of the presentation, he also made a demo by OpenWiFi. As he mentioned, currently OpenWiFi is the only available open Wi-Fi design you can have currently. For the rest, all the Wi-Fi chip, you need to do reverse engineering to understand it. But with OpenWiFi, you have all the code, from Linux driver to the RTL code in Verilog in IPGA. And the second link is another presentation made by me for the Liberal Planet 2021. Here are some real-world examples. This is a Broadcom Wi-Fi 4 chip. According to the reverse engineering, there is an ARM processor. There's a D11 core running the low-level MAC layer protocol there. There are also radio and RF. But of course, everything are secret. You need to do reverse engineering, and you can find more information on that link. This is another example from Atheros Wi-Fi 4, again, Wi-Fi 4 chip. There are ARM processor and some low-level real-time cores for the MAC layer processing. Also, the radio RF there, as you can see, right? But the good thing is that at that moment, before the Atheros was acquired by Qualcomm, they also released the source code of the ARM processor in this chip. But it's far from fully open because below ARM, there are also some other real-time cores running the real-time operation of the Wi-Fi. So why, starting from Wi-Fi 5, there isn't such an open information anymore for Wi-Fi chip? Why is that? Because starting from Wi-Fi 5, the standard and the chip becomes much more complicated than before. Starting from Wi-Fi 5 and 6, now Wi-Fi 7 product already available, right? And you also have to do the backward compatibility, which means Wi-Fi 7 chip is 1 plus 2 plus 3 until 7, not 7 only. So you can imagine how complicated it is inside a Wi-Fi chip. And another interesting observation is that even for RF chip, we thought RF mainly the analog, right? Analog processing. But actually in many RF chip, there's also a controller inside, running program inside. Some of them mentioned in the datasheet. Some RF chip, they didn't mention anything about the processor in the datasheet. But actually, we can observe the RF chip can also get deadlock by some analog signal, which means there's program running inside. Anything that can go wrong will go wrong. Wi-Fi chip is so complicated, so you can imagine there could be many bugs or vulnerabilities, right? Such as this vulnerability reported by Google Project Zero in 2017. They found a new attack way, attack the application processor running code silently on your Android phone while a Broadcom Wi-Fi chip the attack jump over the air, just stand next to you over the air to the Wi-Fi, then in your Android application domain, running code silently. So Wi-Fi is not just a dumb device. It's very weak. Here's another vulnerability reported very recently, right? This year in June. Same story, but this time the target is the Windows computer. The only condition is proximity, and they can run code silently on your computer via Wi-Fi. So previously it's about security, now let's talk about the privacy. You might not know that currently Wi-Fi is used not only for communication but also for sensing, which means by receiving Wi-Fi signal passively, pure passively, you can be located and tracked. And your activity can also be recognized, walking, sitting, or dancing, by purely receiving Wi-Fi signal. And even they can recognize your typing on the screen or keyboard by receiving Wi-Fi signal. Because any activity you will impact the Wi-Fi signal in the air. Those are amazing research, but also bring lots of concerns, right? So I think for security and privacy reason, we do need a very transparent or open design of the Wi-Fi chip, because we don't know how many secrets are there and what kind of things you can do, besides the communication. Next, I will talk about how open Wi-Fi chip could help the optimization or customization of the communication link. So here is an example. Actually, nowadays in the Wi-Fi chip or in the standard, already many configurable options or knobs has been defined in the standard, also in the chip, like the photo I took on the left, right? Like the cockpit in an airplane. There are many knobs. But as a user, only thing you can do is take a seat on the right. Can we try to tune some knobs in an airplane? Don't make me wrong. I'm not telling you to hijack airplane, but you know what I'm saying. Of course, you can tune the knob in an airplane if you have enough money to have a private jet, right? Okay, I don't know whether I can because I don't have private jet. Okay, for Wi-Fi, actually, for normal daily life, I won't complain. It works well. But actually, on the right, for many special applications, such as the industrial or the replacing some very heavy cables by wireless in the industrial automation domain, there are many requirements to customize or optimize the wireless link for their non-consumer use case. But with commercial Wi-Fi, it's not doable, right? Because commercial Wi-Fi chip, there are many knobs, but you can't tune it unless you have many money to buy a design and do it by yourself. This is what is available on the Wi-Fi. This is Wi-Fi 7 or Wi-Fi 6 router. Okay, what can you do with commercial Wi-Fi device? Just you can switch on or off some feature. That's it. And they also recommend you, these are professional settings, don't touch it if you don't know what is it. Or you can do reverse engineering. So I believe an open source Wi-Fi chip will enable the optimization and the customization for many special non-consumer use cases. For education and research, of course, open source project is always the most popular option. I like this sentence very much. What I cannot create, I do not understand. So the best way to learn Wi-Fi technology is do it like us, do it from scratch or study the source code. I think reverse engineering is not the most efficient way to learn how Wi-Fi chips run. Actually, in the 4G, 5G research domain, it is already the case. On the left, there's Open Air Interface project in France, initiated in France. On the right, there's a SRS RAN project initiated in Ireland. These two projects, they try to build the mobile communication stack from scratch, from physical layer to the MAC layer to the core network. So now there are already a big community around these two open source projects. And in US, of course, there's Open RAN Alliance. They already try to push the open equipment in a cellular access network. Of course, these two projects, some of the Open RAN equipment also use these two open source projects. Okay, it's all about software in this cellular domain, open source cellular domain. Of course, not all software are open source, such as this famous software company, Amarisoft, which was co-founded by Fabrice Bellat. They have the most efficient cellular communication stack in x86 CPU based on software-defined radio. That's normal for Bellat, right? Bellat is Bellat. No one can beat Bellat. But why can't we do this software implementation for Wi-Fi? The answer is very direct. Implementing Wi-Fi is more difficult than implementing cellular. Here is a small example. Why? On the top is the cellular system in LTE or 4G. After the base station send a frame, the base station already expect the acknowledgement after 4 milliseconds. So in this 4 milliseconds, so the other side, the receiver can do the demodulation, header passing, construct the acknowledgement sending in computer, because you have 4 milliseconds. And you can't send it early or later. Everything are scheduled. That's the cellular system. So you can do it in software, because the antenna signal to your computer only take maybe 100 microseconds. For the rest, you can do the rest in software. But for Wi-Fi protocol, it's very different, because Wi-Fi work in a shared channel, ISM band. All the stations are equally compete the channel. You can't schedule a response after 4 milliseconds. That's too long. Every other people will wait for your transaction finish. So in Wi-Fi protocol, after you send packets, you expect the acknowledgement from the other side in 16 microseconds. So there's no time for your software in computer to make this 16 microsecond acknowledgement speed. It's too fast for software. So you have to do it in a chip or FPGA. So that's why you can't see many activities in this open source Wi-Fi implementation, except us. So I think for education and research, there is a missing puzzle. Okay, now we have the puzzle. So that's partially the reason why we do the Wi-Fi implementation. So now let's talk about what we have done. This is some photo from FOSDEM 2020. People are really very interested in the design. This is dark history, so you see new people are continuously coming to the day. Here are some users we discovered on GitHub, but I don't know how many silent users are there. Here are some statistics. We are rank 3 of the Verilog topic on GitHub. I think maybe nowadays Verilog is still the most popular chip design language. Here is the hardware currently we support. All the hardware we support like this. There's a RF chip from an analog device on top, and a baseband FPGA from Xilinx. In the FPGA, there are ARM processor running Raspbian, like the Raspberry Pi Linux. Also, the Wi-Fi implemented in the FPGA fabric. So in the Linux, you will see a standard Wi-Fi interface, just like any other Wi-Fi chip. We support the Wi-Fi 4. Beginning is AG. The N is founded by NLNet, thanks to NLNet. Then we have some progress in the new standard, but we still need lots of resources to do that. And we test the performance by very professional instruments, conducted test and over-the-air test. So the performance published on the GitHub is, you can trust it. Let's take a close look what is inside the design. Okay, this is the whole SoftMac architecture in Linux. The yellow one is Open Wi-Fi offer, SDR driver and IPGA and some user space tool. In the IPGA, okay, there are many building blocks, but it looks like quite different from the Broadcom or the Atheros example, right? Because I do the forward engineering, not reverse engineering. At that moment, I didn't realize those information from Broadcom and Atheros. Anyway, there are physical layer, MAC layer, RF control, everything you need. Otherwise, it can't function as a normal Wi-Fi chip. Let's zoom in the two tiny blocks of the physical layer. Again, there are many physical layer DSP blocks, and also very complicated state machine to control. Yeah, for each block, I can zoom in again. You will find more block. So it's very complicated design. The complication not only in IPGA, but also in the driver. As I said before, starting from Wi-Fi 5 and 6, Wi-Fi becomes more complicated. This is one of the reasons is about the multi-user packet scheduler. Because we use SoftMac, which means we can do the packet schedule in the software, in driver. But before Wi-Fi 5, you only decide which user packet come first. It's a time domain scheduling. But starting from Wi-Fi 5, 6, 7, 8, they add more dimension. You can compose multi-users data and assign them to different frequency or different spatial stream at the same moment. So the scheduler becomes much more complicated. So that's why after Wi-Fi 5, including Wi-Fi 5, all the Wi-Fi chip are full MAC, not soft MAC. They bake all the complication into the chip. But if you go for Open Wi-Fi, we still offer the software packet scheduler option there. You decide how to schedule multi-user packet. We also work very hard to push the price lower in the past 4 years. At the beginning, the platform is very expensive, right, from selling an analog device. And we work with hardware makers, hardware communities. Now you can get the $330 hardware from crowdfunding website. So this push a lot for the Open Wi-Fi adoption. And I have to mention that $330 is much expensive than a Wi-Fi dongle, right? But you can't imagine that currently you can have such a price with all the source code of Verilog, Linux driver, and IPGA RF in your hand. Before our effort, I don't know the price. The price must have been at least 100,000 volt, and of course, with lots of NDAs. So this is our contribution to the security research. People mainly use our design for Wi-Fi fuzzing tool. Before the project, they used a commercial chip, but commercial chip, they could just go off the market, or after update, their tools doesn't work anymore, so they like our design because they know the source code is always there, they can trust it. We also have some effort to protect the privacy of the user's information. Like I said, they can do Wi-Fi sensing to locate you, but we have some open source code to make the result random. But for communication, it's still okay. But for localization, those unauthorized people only get random results. And for customization of the Wi-Fi, we do observe lots of activity there. Here are the snapshot of the issues on GitHub. Many people ask, how can I change the bandwidth from 20 megahertz to like 2 megahertz or 5 megahertz, right? And seems like some people already succeed. See, file transfer after reducing the bandwidth. So before our project, it's not possible because commercial chip, you can't change anything. These are in the research and education domain. There are lots of papers based on Open Wi-Fi, not necessarily all from our lab, also many of them from other university and institutions. Here is a very interesting example. One guy already started to study how large language model could assist the wireless chip design. With our code, they can do such a study. Without this set of code, I think it's very difficult for them to do such a study, right? Because you can't get the code from big company and publish the research on it. Here are some other examples about security and privacy research. The Jasper is a very interesting example here for education. He did the Wi-Fi 5 fuzzing master thesis with us. After the master thesis, Jasper said he will never do FPGA development anymore in his life. Very painful. But we do inspire him to do Wi-Fi research. Afterwards, he created the ESP32 Open Mac project, which is very hot now for the ESP32 Wi-Fi module reverse engineering. So how to move forward? Actually, I don't worry too much about reinventing the view because no two views are ever exactly alike, right? We do forward engineering, so our view must be very unique and different from those views from big company. Okay, talking about big company, I don't have answer, but I do try to find some clue in the history how a small project grow. But maybe competing with big companies shouldn't be our current focus, right? As long as we can focus on what we do the Wi-Fi in the way we like, right? Make it more secure, more protect the privacy better, make it more open for tuning, customization, for research and education. And last but not the least, make it long run, right? Because we always maybe try to overestimate the impact in short run, but we always underestimate the impact in long run. So the last jump, right? Jump from FPGA to a real chip. Shall we take the leap of this faith? I think there are at least 3 reasons. The chip could lower the cost a lot, right, compared to FPGA. Maybe from $330 to $3, I don't know. And it could turn this set of FPGA Verilog code be silicon proven, right? Doesn't matter is the open source EDA or closed source EDA. This set of Verilog code could have some solid proven. And I agree with the previous presentation. I think even for open source EDA tools, you really need some serious, very complicated design, right? Such as the Wi-Fi or the previous CPU, Linux-capable CPU. So that's why we need to take the leap of the faith. Of course, there are still many works to be done. Even in the IPGA branch, currently we focus on the maturity and the performance of this set of Verilog code on top of IPGA. To prepare for the future, we still need to replace some Xilinx IP core and generate more comprehensive verification vector, do the certification test with the Wi-Fi Alliance, adapt some interface IP for the future. And on the central, maybe the first step, we can do a pure digital baseband chip. We still leave the RF flexibility to the user because many users actually they want to run the Wi-Fi in some private band or non-ISM band. So maybe some of them told us they like the pure digital baseband. Then they do their own RF in their own band. And finally, we could go for a full chip with RF integrated. Of course, you need all the steps for a typical chip design flow in open source EDA or closed source EDA. So in summary, we need a low-cost and open-source Wi-Fi chip that capture the common requests, such as the security, privacy, customization, tuning. And we also need entity, I think, that capture the common interest of open-source Wi-Fi chip and attracts the continuous funding. We already have a role model in cellular communication, as I said before, right? The Open Air Interface Software Alliance, initiated in France. It's a non-profit and sponsored by Cooperate, and they make a common roadmap, make sure the implementation quality, and also their main mission is to increase the adoption of their design. I think we also need such an organization or entity. We are considering try to set up this. Of course, we definitely need many support from partners and community. Yeah, that's it. Taking questions. Thank you.
Any questions?
Hi. For instance, if we add a CPU inside the design, could it replace like cellular communication by being as low power or as power efficient as regular modems, like 5G modems, for instance?
You mean you try to add CPU in this design?
Yeah, for instance, if people run community Wi-Fi networks, can we like get rid of the 5G networks and replace it by Wi-Fi? That requires basically a modem that is low power and very efficient. Could Open Wi-Fi bring that somehow?
Yeah, I think that's kind of customization. Customize the Wi-Fi to the use case, to the traditional cellular use case, right? Yeah, I think you could try that, but you should realize the cellular technology, they have been working in this domain for many years, right? Now you try to rediscover many issues as done in the past many years, starting from Wi-Fi. I think Intel ever tried that, the WiMAX. It's from a computer science point of view, they try to push the wireless communication to the operator level, the WiMAX. I think that's the kind of similar trying, like based on Wi-Fi, offer the broad connection to more people. That's not a so successful try, but since you have source code there, so it's your decision. Yeah.
There's another question here.
Could you say something about the signal processing algorithms that you're using, how you evaluated that, how you made that, on which platform, and is it all also put just onto the same GitHub as MATLAB or something?
Yeah. Actually, we follow very similar procedure as how industrial does it. We're starting from the algorithm design in MATLAB, floating point algorithm. Then we make a fixed point algorithm in MATLAB to find out what's the performance loss, right? From fixed point in MATLAB, we go to a Verilog simulation, to make sure the Verilog simulation is fully aligned with MATLAB algorithm. Yeah, and finally test with over the air or the RF test the actual performance. Yeah.
More questions?
Hi. You mentioned that you used Xilinx IPs. Is that used in this digital baseband, or it's only in the DMA, so DMA or something like this? And if you use this Xilinx IP, are they free or the paid one? Because I know that Xilinx have some paid library.
Yeah. For instance, the FFT module. In the transmitter, we use the open source FFT module. In the receiver, we use the Xilinx FFT module. But FFT is for free as long as you run the IP core on Xilinx FPGA. Of course, you can only run Xilinx FFT on Xilinx FPGA. For 8-bit decoder, we also use the Xilinx core. There are also some free version. Some master students already tried the free version of 8-bit decoder. But when we use Xilinx 8-bit decoder, you can have an evaluation license for free from Xilinx. Then your design run like 2 or 3 hours. After 2 or 3 hours, you need to reload FPGA.
Do you have any feeling here? Do you have any feeling on how many patents you might have infringed?
Don't answer the question.
You should ask Philip. Yeah, I think those in the cellular domain, they have the same problem. Or I don't know whether it's a problem, because in cellular domain, there are open air interface and SRS LTE. As you know, the 3GPP, their patents are much more valuable, right? There, yeah.
Okay. More questions?
Okay, thanks. My name is Arndt. It would be highly attractive to increase the transmission power. Is this sort of easy with an openly designed hardware? And if not, how do you prevent the user from turning it into a much more useful device?
Yeah, currently the analog device chip transmitting power is very low. It's about several dBm, but Wi-Fi OFDM waveform, you need a big backoff for to make sure the peak won't go to the nonlinear. After backoff, I think now the transmission power is like minus 13 or 14 dBm. It's a macro power. You need to add external PA. But even with this minus 13 dBm, you can already communicate via 5 meters, no problem for your fun. But some people ask the similar question on the GitHub. We point them to another analog device module, could boost the power by like 20 dB.
More questions or comments? If not, let's thank the speaker again.